Alright, hi everyone. Today I'm going to present on quantum machine learning, QML. Yeah, here's some introduction. Machine learning has revolutionized various fields, including computer vision, NLP, and so on. Deep learning is a subfield of ML and has achieved remarkable success in these areas. And in classical deep learning, you have things called artificial neural networks, inspired by the structure and the function of human brains. ANNs are the foundation of deep learning. Yeah, they consist of interconnected layers of neurons that process and transform information. And some of the strengths is that it can do feature learning from large datasets, it can do pattern recognition, and it's also effective in multiple applications. And, but then, classical deep learning has some limitations. For example, yes, for high-dimensional data, classical models struggle with data containing a large number of features, leading to issues like the curse of dimensionality. Yeah. There's also a limited expressive power. It struggles with complex relationships in high-dimensional data. There's uh, there's also a limited amount of uh, representation in complex relationships. Capturing intricate non-linear relationships between data points can be challenging for classical algorithms. There's also the issue of scalability in training and deploying deep learning models. Uh, yeah, so basically the larger the size of the data, uh, the larger the model has to be to kind of like take it in, and then because of that, right, it doesn't scale that well, and then the more computational power is needed. And then uh, in the classical world, where uh, they usually use bits, and it has a limited kind of expressive power compared to qubits in the classical world. Yeah. So, QML is a rapidly evolving field that explores the intersection of quantum computation and machine learning. QML aims to leverage the unique properties of quantum mechanics to enhance capabilities and potentially overcome the limitations of classical deep learning. And QML has certain unique advantages coming from quantum mechanics, namely superposition. Qubits can exist in multiple states simultaneously, potentially offering an exponential increase in information processing compared to classical bits. Yeah. And QML models are able to capture more complex relations with fewer parameters, so you can expect QML models to be smaller. Yeah. And so there's an improved in efficiency of handling high dimensional data by exploring multiple possibilities simultaneously. So in the classical world, right, if you want a large amount of data, right, you have to actually uh, input all the large amount of data. But in quantum, right, you can actually create a superposition of all those data, and then you end up having only a small input. Uh, yeah. There's also entanglement, where QML entanglement allows QML models to potentially capture more intricate interactions between data points more effectively. In the classical case, right, you only usually have things like linear combinations and also inner products, which is more limited uh, uh, in its expressivity. Quantum mechanics is also more scalable, as certain QML algorithms shows promise for solving specific optimization problems with potential efficiency gains over classical counterparts. Yeah, so QML can be understood as quantum enhanced machine learning, using quantum algorithms on quantum computers to improve upon classical machine learning techniques. Yeah, basically you uh, substitute certain parts of the workflow of classical machine learning with uh, quantum algorithms. Yeah, and current it seems that performing machine learning purely in quantum is not feasible, and only certain parts of the process can be theoretically replaced by quantum approaches. And the QML workflow consists of like three main parts, roughly encoding classical data into qubits, and because your quantum computers needs inputs in the form of qubits, and but usually your data is in the form of classical, yeah, and two is to feed the data into the quantum computer, and then from there you can apply your QML algorithms, and the third is to measure the output, and then from there right, you can use the output for whatever purpose you want, be it like classification or regression. Right. Now we compare the in classical versus quantum systems. KNN's classical neural networks are computational models using quantum mechanics for neural networks capabilities. It is inspired by classical neural networks. How QNNs differ from classical neural networks? In terms of information processing, QNNs use qubits instead of neurons, and it uses quantum gates instead of activation functions. And these qubits, it can exist in multiple states simultaneously, known as a superposition, and it allows for parallel processing of information. These quantum gates, it can perform operations on qubits, enabling manipulation and transformation of quantum information. Yeah. In the classical neural networks, right, you have things called perceptrons, which you can think of as the simplest unit. It performs linear separation of data together with an activation function, and it's limited to the am I ignore that. And you can actually stack multiple perceptrons together to create this thing called a multi-layer perceptron, or MLP for short. And then this together with the non-linearity, right, enables non-linear decision boundaries. Yeah, and there's also activation functions, which is like these non-linear functions. And yeah, so these are kind of like the essential components in your classical neural networks, and it's like used everywhere. Some differences in terms of information representation. CNN's classical neural networks, they use floats as the basic units of information. So usually what they use is a 16-bit float or 32-bit float to represent the inputs. Whereas in QNNs, they use qubits, that is a superposition state, and it's usually measured in the standard basis of 0 and 1. And this actually allows for increased information storage and processing. Yeah, in classical case, you only have like 16 or 32 bits of information, while in the quantum case, you can have indefinite amount of information within the qubits. In terms of computations, classical neural networks, they apply an activation function and to a weighted sum of the inputs from the previous layers. Yeah, so let's come down here for a while. This is what a classical neural networks look like. So each of these nodes is like the perceptron, and it has multiple inputs, and all these inputs, right, is multiplied by a weight function. You can think of it as the lines over here. Yeah, and then from there, right, the value of this node, right, is a linear combination of all these uh, outputs in the previous layer. Yeah, and then you apply an activation function to the value here, and then before the value is like passed on to the next layer. Yeah, but then in QNNs, you don't really have all these activation functions. Instead, they utilize quantum gates such as Pauli X gates, Hadamard gates, CNOT gates to manipulate qubits and perform computations. These gates can create complex entanglements between qubits and enabling them to influence one another. Yeah, that's good. So this is roughly kind of how a quantum neural network looks like. You have your input qubits over here, and then you can roughly split the QNN into three components. Over here the fx serves as a encoding layer, and the AX acts as a variable layer, a layer with like parameters, where you can vary it, and the O functions as a measurement layer. Yeah. Here's more images of what it looks like over here. The input encoding, and this is the trainable layer, and then you measure at the end. So let's talk about quantum variational circuits, the quantum analogous of classical neural networks. Quantum variational circuits emphasize the optimization of circuit parameters to perform specific tasks. So in the classical case, right, you have your neurons over here, and all these weights can be adjusted to get the output that you want. For example, when you pass in an input, then you get a certain output, right? It may not be exactly what you want, but then in training the model, right, you can actually adjust all these weights, right, to make the output more towards what you want. So this adjustment of the weights, right, is the variable part that is why it's trained. And so the quantum version of that, right, is this variational circuit, this circuit that can be trained. There are a few components of this classical variational circuit. First is the quantum feature maps. It transforms the classical data into quantum states within a high-dimensional Hilbert space, which can be processed by quantum computers. So, essentially, your input data usually is classical data, but the quantum computer, it expects qubits, so you have to like turn the classical data into qubits. How you do that is by quantum data encoding. And there are many ways of doing it. Here are the three main ways, the most popular ways. First is basis encoding. Is basically you have a certain preset precision that you're aiming for, and then the first bit is taken to be the sign. So let's see an example over here. We have this float vector over here, and for 0.01, the first bit is a 0 since it's positive, and next the 0001, it represents 1 over 16, and so this 0.1 is approximated by this 1 over 16. And over here negative 0.7, since there's a negative, we represent it by a 1 over here, and the 0.7 with this 1011, which corresponds to this, which is approximately 0.7. And so this vector, the classical data, is now converted to this state, this qubit state. A second method is angle encoding. Now this is the most or at least a very popular method in research. And what it does is basically to use a rotation gate to rotate the qubit, right, proportional to the vector. And you can probably imagine that this actually is more accurate as compared to the one above over here, as it doesn't lose any information, since rotation it can be like continuous, whereas over here there's some approximation, it's not exactly the same, so there's a bit of information lost over that. There's a third method called amplitude encoding, where you first normalize the input vector to a unit length, and then you pad it by a 0 to the nearest power of 2. Then from there, right, you just take the vector to be the amplitude of the qubits. yeah, and that here you have your final qubit state encoded. Yeah. So after the quantum data encoding, next you have to use entanglement, and this is usually done by applying gates such as your polyrotation gates, Hadamard, or control operation gates. And uh, there's actually many different ways of doing this, and the specific pattern and degree of entanglement depends on the application requirements, and is usually determined by the researchers using by making a intelligent guess. Yeah, and here we have just some examples of this entanglement layer. And you can see it's kind of like a lot of connections, basically trying to entangle everything. Yeah. And there are many different ways of doing this. And yeah, it really takes the kind of expert to try to decide on what would work well. Yeah, there's a challenge of like choosing one an effective circuit that represents the solution space while maintaining a low circuit depth and number of parameters. And you want a low circuit depth so that the amount of error will be reduced. Yeah, the amount of noise. Yeah. Yeah, and next uh, yeah, we have the variational quantum circuits. So all the stuff above here, right, is static. It doesn't change. But then we want the Q and N, right, to actually learn. Uh, yeah, and the way it does it, right, is by having all these circuits where you can uh, like vary the parameters, and then from there, right, you can learn what the right output is. So yeah, it's the part that can learn. Variational circuits are parameterized circuits where the gate sequences are optimized to minimize a cost function. Classical activation functions are replaced by quantum operations like rotation and control gates. Yeah, because in the quantum world, right, you don't really have all these non-linearity activation functions. Yeah, and yeah, this variational circuit actually has different names depending on the context. In some places, they call it the parameterized quantum circuits, and there are quantum circuits that have tunable parameters, and these parameters are usually angles that determine the rotations of qubits. Yeah, so all these are usually like rotation gates, and in some places they also call it the ansatz, uh, which is kind of like a guess, a hypothesis, an intelligent guess. In terms of the the types of gates and their arrangement, all these are usually determined beforehand by the researchers through an intelligent guess. Yeah, next there's training. After you have your variational circuit, right, how do you like tweak it to improve it? Uh, in classical neural networks, right, they use this thing called backpropagation to adjust the weights based on the difference between the predicted and the actual outputs. So, you have classical neural networks like this. Let's say you pass your input through, and then you get a certain output. Let's say it says low, but then your desired output is actually high. So there's a bit of an error there. What backpropagation does, right? It tries to figure out why what's causing the output to be low. So it could be, for example, that this node is actually saying low. Then what backpropagation does, right? It maybe try to decrease this weight so that the output would be more high. You know, yeah, and you can actually go a level further by looking at why this node actually predicted a no by looking at all these nodes in the layer before. Then you can see like maybe which are uh, the, the neuron that like contributed to this neuron predicting a low, and then you can change the weights accordingly. Yeah, so that's how classical neural networks are trained. But then to do that, you need gradients to find out like how much of the contribution of the output, right, is contributed by a certain neuron. Yeah, but the problem is that you don't really have gradients in the quantum world. Since all the gates are unitary gates, yeah, you don't really have gradients. So for QNNs, right, in order to train it, there are many different methods, including like meta optimization algorithms to optimize the parameters in the quantum circuit. Uh, yeah, and then after you optimize the parameters, right, usually they use classical optimization algorithms like SGD outside of the quantum computer lah. This is the classical case to train the classifier. And in training, right, you have a few steps. First is you need to measure the loss, and then um, how this is done, right, is usually they have to sample the output of the classical circuit multiple times to kind of like get the output uh, distribution. Yeah, and then from there, right, you can use standard classical loss functions, for example, cross entropy, to determine the loss. Yeah, and for to backpropagate the loss through the quantum circuits, right, instead of backpropagation, right, they use parameter optimization. So the quantum world, there's things like parameter shift rule, where you estimate the gradient by slightly shifting the parameters and observing the change in the output. Yeah, since you don't have gradients in the quantum world, so uh, what they do is they pass the input through, and then they sample it multiple times to get the loss, and then after shifting the parameters, you measure the loss again, then see how the loss change, and then from there you know how to tweak the the parameters in order to improve the quantum circuit. Yeah, and you might be thinking to yourself that there's highly inefficient, and that's true. And there is a lot of work in trying to make this more efficient. There's things like stochastic parameter shift rule that uses random sampling to try to improve the efficiency of this uh, updating kind of algorithm. So that's how a quantum variational circuit works. Let's see in action over here through this quantum kernel methods. Quantum kernel methods introduce a quantum enhanced way of uh, processing data by mapping classical data into quantum feature space. This method utilize the superposition and entanglement properties of quantum mechanics to perform classifications or regression tasks using quantum variational circuits. So you can think of this as the quantum version of support vector machines. Yeah, and how this works is usually in the classical case, right, you have your raw data, then you pass it through a what they call a kernel function. And what this does is it maps your data into a higher dimensional space, and then you can learn a hyperplane to try to like uh, bisect all the points in the higher dimensional plane. So in the QSVM, what they do is they pass the data through a quantum encoding circuit, yeah, to map it into the quantum Hilbert space. And then after that, right, you can do the same thing in the classical, right, where you try to learn a hyperplane to dissect the data. Yeah, so the kernel function is basically just to map the data to a higher dimensional space. The So in the quantum world, right, the kernel function, it allows explicit feature map computations. It allows for infinite dimensional data encoding, and it depends on data. It does not specify the feature map explicitly, meaning that the quantum kernel function, right, is fixed, it's not learned. Yeah, it's not a quantum variational circuit. And yeah, the advantage, right, from quantum kernel methods is the ability of quantum computers to efficiently compute the kernel function for quantum data, which could be intractable for classical computers. Yeah, if you have a really big kernel function, or for like big input, right, to map to a big uh, output space, right. Yeah, it could be intractable for the classical case to like emulate. So QSVM is like a very simple kind of example of machine learning. So let's look at something more uh, advanced. Here we have QCNN, Quantum Convolutional Neural Networks, which is the quantum analog of classical convolutional neural networks. This architecture is inspired by the convolutional networks found in classical neural networks. Classical neural networks do something like this. You have an input, usually an image, and then you have a certain uh, window of sorts that takes a grid of the small subset of the input and applies a kind of linear combination. Yeah, it's actually like multiplying it by a matrix and applying a activation function to get to the next layer. So that's what they call a convolutional layer. There's also a pooling layer where you combine a few of the elements down to one. And there are different ways of doing this. You can do things like mean, sum, or finding the max, which is the most popular one. Yeah, it's called max pooling. Yeah, and you just repeat this convolutional and pooling layers a few times, and at the end you have a fully connected layer. You can think of it as like a linear combination of the output to get the final output. And here is one example of an implementation of a QCNN. Over here you can see like this 2-qubit interrogate, which like is like the convolutional layer. And over here we have this little system here where you measure one of the qubit and then use it to control another qubit. Yeah, this acts as a pooling layer. As you can see, the input here is like 8 qubits, and then after the pooling you reduce it to 4, and then similarly you can repeat this a few times, then yeah, we have final like fully connected layer at the end. But there's also other ways of implementing this QCNN. Here is one called the MARA, multi-scale entanglement renormalization ansatz. It looks something like this. Yeah. Here there's an example of a QCNN. Here at the front they use a classical CNN to do the convolutional and max pooling, and at the output here they pass this output into several parallel layers of your quantum variational circuits, and then finally the output of those, right, are passed through a final classification layer in the classical. Yeah. And here you can see their methods. They use the anchor embedding, which is like the most common kind of methods. Yeah. And then they use rotations within the quantum gates and in the parameterized circuits. Yeah. And they use CNOT operations to entangle the qubits. And yeah, they also there are different ways of optimizing the variational circuits. For example, the parameter shift rule, the adjoint differentiation, or backpropagation, which is not possible on a real quantum computer, but usually all these are implemented uh, in on classical computers, so you can actually train it uh, using backpropagation just for research purpose. Yeah, it's can't currently can't really be implemented in an actual quantum computer. Yeah, and they found out that uh, their 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 quantum version of CNN achieve a higher accuracy while using fewer parameters, which means that their model is smaller. Yeah, and the way they are able to do this right is the quantum circuit is able to learn more intricate calculations and uh, be able to learn them using fewer parameters. Here there's another implementation of a QCNN, and in this case they use this thing called a convolutional layer. Basically what it is a fixed non-trainable quantum circuit, and then yeah, it's a circuit that's over here that's not trainable, and then after that right they take the output and then pass it through a fully connected layer. Yeah, for classification. Yeah, and they also found out that similarly it produces high accuracy. uh, yeah, so as you can see right, there are many different uh, ways of implementing CNNs in the quantum world. Um, Basically, this whole field of QML is not really that developed, and there are still like many different ways of doing things. There's not really like surefire kind of decided way, best way of doing things. All this is still under a lot of development. Yeah, and here you can also see a lot of different kind of models that are being explored in the QML. Yeah. So let's talk about the current state and some challenges. While QML is a promising field, it's still in its early stages of development. Several challenges need to be addressed before widespread adoption. First, there's the limited hardware. Quantum computers are still under development with limited availability and scalability compared to classical computers. As you know, yeah, there's a big limit in the amount of quantum hardware there is, and so a lot of all these QML algorithms right are not actually uh, run on quantum computers, and it also really limits the applicability of all these QML algorithms. Yeah, there's also the issue of error correction. Quantum computers are susceptible to errors, and robust error correction techniques are crucial for reliable QML applications. There's also the issue of data conversion. The practicality of QML is often limited by the conversion of classical data instructions into a format suitable for quantum algorithms. Yeah, so in most practical applications, right, the data input that you have, right, is classical. But then in order to utilize this QML, right, you have to convert it into qubits. In some cases, right, the amount of overhead in converting the data, right, is actually more than the amount of benefit that you get from utilizing QML as a compared to its classical counterpart. So yeah, it really uh, defeats the purpose of using QML. Of course, there's the case where your data is already in the form of uh, qubits, in which case there's no need to uh, convert it. And despite these challenges, QML holds immense potential for the future. As hardware capabilities improve, algorithms, virtual and theoretical understanding deepens, we can expect advancements in quantum circuit learning. Uh, so basically, instead of using the ansatz, the educated guess approach to creating quantum circuits, right, you can actually learn what is a good quantum circuit for specific tasks. Yeah, it makes all this QML more approachable. There's also circuit design. You know, in the classical world, right, there are different kind of deep learning models such as your autoencoders, your RNNs, your transformers. And it makes you think whether there are the quantum counterparts to all these models. There's also algorithmic development, designing efficient and effective quantum algorithms for specific machine learning tasks. Yes, interpretability, understanding the decision-making process and potential biases in QML models. There's also hybrid approaches, combining classical and quantum techniques to leverage the strengths of both worlds for the optimal performance. Yeah, but this still needs a lot of research to find the optimal balance between the two. And finally, there's tackling complex problems. KML could address tasks that are intractable for classical deep learning, especially in areas like material science, drug discovery, and financial modeling. And this is really exciting as you know quantum algorithms such as the Shor's algorithm that's able to uh, do operations that are intractable for classical computers. It really makes you think if there are some classical problems, right, that seem really difficult, right, that perhaps quantum machine learning could solve, and that would really uh, it will be a huge advantage, and it's really exciting. And in conclusion, KML is still under development and its practical applications are limited by current hardware capabilities and ongoing research in algorithm design and training. Even so, KML holds immense potential to address the limitations of classical deep learning, and as research progresses, KML could revolutionize various fields by tackling complex problems and exploring new solution spaces. While KML holds promise, it is not a complete replacement for classical deep learning, but rather a complementary approach with potential benefits in specific areas. Yeah. Cool. This is weird time. Let's look at this website. Yeah. And this is the library in TensorFlow for implementing quantum neural networks. Here we have an example of quantum convolution neural networks. Yeah, let's just go through this notebook. Here they import all the required libraries, and here they are going to build the circuit. Yeah, start by appending all the different unitary gates. Yeah, this is the circuit that they want to design. Create the data. And here they create a cluster state, which is a highly entangled state. And this is the entanglement layer that they have. You can see like every qubit is like entangled with each other. Here they add the CNN layers. Yeah. They display the layers. A very long QCNN layer. Yeah, and here they train it using backpropagation, which can be done since this is a quantum simulation in a classical computer. Yeah, and here there's a hybrid model with a quantum input and then a classical classification layer. The hybrid model converges faster than the purely quantum version. Yeah. Very cool. So there are other notebooks as well that you can explore if you're interested in. It looks very interesting. Yeah. Thanks for watching. Like and subscribe. Special thanks to my Patreon.